What up, fam? Let's get going. Get this AP review video. Let's do it. So, each one of these questions you can see, like it says, which of the following is equivalent? So there's going to be multiple choice on the actual test, but I figured for the video, there's not really a need for this multiple choice. So let's do it. It says, let X represent a random variable whose distribution is normal with a mean of 150 and a standard deviation of 12. So just as a reminder, if you see this on the AP test, it will look like this, where you have N, parentheses, and then 150 comma 12, or it could show up like that, and that means a normal distribution with a mu of 150 and a standard deviation of 12. And this is which of the following is equivalent to the probability of X being less than 144. I think it's a good idea to have a visual understanding of what's going on. So we're going to draw a little version of a normal distribution. There we are, where our dead center value, our peak value, is going to be 150, and that is also the mean for this question. And then continuing on, we also have the idea of a standard deviation being 12. So on both sides, it's going to be exactly equal. That fancy word, the inflection point of calculus, where it goes from a happy face to a frowny face, or from a frowny face to a happy face, that's going to be 12 away. So like 162 adding 12, or 138, what did I write, negative 138 subtracting 12. So this is going to be like a basic setup of it. It actually goes further out. That's only one standard deviation. It goes out forever in both directions. Technically up to infinity and negative infinity. But for us, the only things that are going to matter are kind of in between, because it wants to know what is equivalent to the probability of being X less than 144. So I'm going to go ahead and change colors really quick, just the pink. And I'm going to specifically put the actual probability here on our graph is going to be less than 144. So visually, 144 is going to be smack dab in between 138 and 150. It's exactly 6 away. So we're kind of looking at this area as to what things could be equal to it. So if you're looking to see what's equal to it, the most obvious one for a normal distribution is going to be on the opposite side that is exactly the same concept. So because that 144 is precisely 6 away from that 150, then the positive side of it, that is to say, if it was bigger, I'm going to go ahead and do it in, how about a green color here? Really hope no one's colorblind watching this, because you will struggle with the blue and the green, but I apologize to you. So you have X greater than 156 in green here. And what that's going to do is 156 is going to be 6 away on this side. So we can see that's going to be one version of what's going to be exactly the same. However, you can also do 1 minus something to figure out what's going to be exactly the same as the probability of being less than 144. Let me take a drink really quick. I'm going to pause. Okay, we're back. So, like I said, we could also do a 1 minus something. That 1 minus something that I would like to discuss is going to be using the idea that because we're kind of like dividing it into two sections here, the less than 144 and the bigger than 144, we could also think about the opposite area. So let's think about the opposite area here. The opposite area to less than 144, just in terms of an opposite area, that opposite area is going to be 1 minus the probability of X less than 144. Now this is not equal. This is going to be a different value, because it's going to be all those values over here. But what about instead one that actually is equal? So I'm going to do it in pink here. One that is equal would be the probability of 1 minus the probability of X being less than 156. So let's figure that out. So less than 156 would be right up to this point. So we're saying all of this, but 1 minus it. So 1 minus it is going to be what's left over. Likewise, I could also do another different 1 minus that would be exactly the same as this pink area, and that's going to be 1 minus the probability of, it's going to be X greater than 144. This is another one that'll be exactly the same as probability of X less than 144 would be 1 minus the probability of X being greater. So this blue one completes it. So this part from this and this added together is 100%, whereas the less than and the 1 minus the greater than are going to be the same thing. I hope that made sense. If it didn't make sense, one thing you could do on a question like this is, because it's going to be multiple choice, you could actually simply calculate what this probability is. Every single one of these probabilities is calculable. So in order to do that on the calculator, so this is all option 1. Option number 2, maybe you're just not feeling this thinking version of it, so you'll spend a smidgen extra time going into the calculator. The calc version, which I'm doing in red here. So the calculator version, let's just do it right here. So we want to go ahead and do a normal distribution. Remember, the only reason we can do this red part is because it says the word normal here. So we're going to be doing our second vars. So we have second vars, and from the second vars, we get the distribution. We're going to hit normal CDF. Here's our normal CDF. And we need to calculate every single one of these kind of individually. So like the original probability was x less than 144 with our mean of 150, our standard deviation of 12. So we're trying to do less than 144. Less than 144 visually goes all the way off to negative infinity. It's this pink one, all the way up to 144. So we can leave that -1 there. However, I kind of like putting -999 for myself. It's just what I like doing. And then for the upper part, we have 144. Our mean is 150. Our standard deviation is 12. And we're going to go ahead and paste, and we get this 30%. So it turns out that this area is 30% of the entire area being 1. Just to show you what I was talking about earlier, if I do 1 minus that number, I will complete the value. So if I do 1 minus this answer here, well, of course I'll get that. But I don't know, 1 minus the answer. Come on. 1 minus the answer. If I do that, these two numbers added together will be 1, but of course they are, because I did 1 minus. So it's going to be a completion of the value 1. After that, so we've calculated the original one. The only one that matters is this pink area, the one that we did originally. We're trying to figure out which one of these was equal to it. So just to show that greater than 1 is in fact equal to it, we'll go second vars, normal CDF. Come on. Why is it not cooperating with me? There we go. Normal CDF. There it is. Now we're doing greater than, just to do this greater than 156 to show it's the same. So our lower is going to be 156. Our upper is going to be like 999. Our middle is still 150 and 12. And we go ahead and calculate it. And sure enough, it's exactly the same value. But now we want to go ahead and do these ones where we're doing 1 minus 1. So we're going to do 1 minus, we're going normal CDF. And now for 1 minus, we're doing x greater than 144. So bigger than 144 there. 999 is good. All those are correct. And sure enough, we get exactly the same answer. And like I said, we could have also done 1 minus the probability of it being less than 1 minus vars CDF in less than 156. So if it's less than 156, our lower is -999. Our upper is 156. Putting it in as a paste. Sure enough, one more value that's all the same. So to make a long story short, every single one of these, and I'm going to underline in pink here. So this is the same, this is the same, this is the same, this is the same. All 4 of those are exactly the same value. And on the actual question, which is actually a free response, it's a multiple choice question taken directly from an AP exam with different numbers. It's going to have 5 multiple choices, and one of them that looks like this will be correct. So either A, do the visual understanding I was talking about, memorizing the setup of the 4 there are, or use your calculator to figure out which one's which. I think calculator is probably going to be the easiest bet, but anyways, we have already spent 8 minutes on the first question. I apologize. Let's move on to number 2. All right, this one's actually going to be a lot easier. It's going to be, did you memorize and write down the formula? Yes or no? Random variable x is normally distributed with a mean of 20 and a standard deviation of 5. So we're going to go ahead and say, this didn't say normal, it says normally distributed. The normal distributed is actually not important for this. The only part that is important for it is the actual mean. So our mu of x is going to be 20. And our standard deviation of x is going to be equal to 5. And random variable y is normally distributed with a mean of 7. So the mu of y is equal to 7. Excuse me. And the standard deviation of y is, what did I write? That's supposed to be capital Y. I apologize. And your standard deviation of 2. If x and y are independent, what are the mean and standard deviation of y minus x? Please note, you can only do this problem if they're independent. If they are dependent variables, we don't go over that topic in AP Stat. It's a higher level topic. I'm sure you'll do it if you do, I don't know, like a math major or something. What are the mean of y minus x? The good news is the mean is super duper simple. The mean of y minus x is just literally y minus x. So 7 minus 20, in this case, negative 13. So straightforward. You don't even have to think about it. You just subtract the two and you're done. Easy enough. The problem is the standard deviation of y minus x is actually the same as the standard deviation of y plus x, and that is going to be the square root of these two squared and added together. So it's kind of like the Pythagorean theorem. So we're going to go ahead and do our 5 squared plus 2 squared. So that turns out to be the square root of 29, or you could have just plugged it into the calculator from the get-go. Plugging into the calculator from the get-go, we'll have second square roots, and then 5 squared plus 2 squared, and turns out to be 5.3852. And again, you could have also just done the square root of 29. That would have been fine too. It's the same exact answer. And that's the whole problem. That is all it's going to ask once in a mean standard deviation. Do you know this formula, yes or no? So again, the mean, you subtract the two just like it is. If it was addition, you'd be adding it. And for the standard deviation part, adding and subtracting are the same thing. Either way, you're going to square the first standard deviation, square the second standard deviation, add those results together, and then take the square root after the fact. Please be careful. You cannot take the square root first and then square root first and then do that. Otherwise, you'll get 7, and that's not right. So be careful. All right. Here we go, number 3. So number 3, an experiment has 3 mutually exclusive outcomes. So as a reminder, what this means, mutually exclusive outcomes cannot happen at the same time. Cannot happen at same time. And if P of A is 0.3, P of B is 0.6, and P of C is 0.1, which are true and which are false. So we got to figure out which ones are true and false. So B and C are independent. That is a huge false. Oh gosh, major falsehood. The reason why it's a major falsehood is they're mutually exclusive. If they're mutually exclusive, that means if one of them happens, you know that the other one does not happen. So they're absolutely not independent, because if B happens, C doesn't. If C happens, B doesn't. False, absolutely not, because they can't happen at the same time. The P of A and C is equal to 0. This is true. And the reason why it's true is because we were told they're mutually exclusive. They can't happen at the same time. So the idea of it being an and, definitely going to be a true statement. This number 3, this third one, is also a true statement. The reason why it's also a true statement is because the and part is equal to 0. So our regular old formula is P of A or B is equal to the probability of A plus the probability of B minus the probability of A intersection B. But this part right here is 0 because it's mutually exclusive, and because it's 0, we have 2 true statements. And on the actual test, it's a very similar question to this, where you have to figure out true or false statements for mutually exclusive situations. Let's move on to the next one. Number 4, Pokemon card printers claim that 96% of cards are perfectly printed. If you buy 1,000 packs of 11 cards each, what is the expected number of cards without errors? So the idea here is that this is supposed to be a binomial situation, and because of the binomial situation, you can use the formula that the expected value is equal to n times p. So let's figure out why it's a binomial situation first, just so you can verify it for yourself. I'm telling you right now in the actual test I'm giving you, it's going to be binomial, so you don't actually have to verify it, but let's do this anyways. Binary, it either is perfectly printed or it's not. So it is error or not. So definitely binary. Is it independent? It doesn't say that it's independent, but we're going to go ahead and assume that all cards printed are independent of each other. You could argue that this is actually a false statement, because if one card has an error, you might argue that the very next card printed after it would also be a higher likelihood of having an error, because like the printer's busted or something like that. So this is going to be assumed. And you're usually allowed to just assume it. However, on the actual AP exam, they like tell you can assume that they're independent. And I think on the question that is on the final, it says that it's independent. So really, when I rewrote this question, I should have said assume independence, but I didn't. The number is set in advance. The number of cards is set in advance. Be careful on this one because I did do a little bit of a trick. It's not 1,000 cards or 11 cards. It's actually 11,000 cards because you're getting you have 1,000 packs of 11 cards each, so you have 11,000, 11 times 1,000 cards total. And the success chance is the same for each card. Yes, we said 0.96, and again, that's assuming that they're independent because, anyways. So yes, we are, and like I said, the expected value for a binomial situation that follows that Bin's idea is just going to be a nice, easy n times p. So in this case, we're going to have 11,000 multiplied by our success chance of 0.96, and that's all you do. You just multiply those two things together, and you're done. So we got 11,000, I missed a zero there, times 0.96, and we have 10,560. Boom. We're done with that one. Done with this page. Moving on to the next page here. We have question number 5 coming right on up. Here we go. So I think what I did was, sorry guys, we are going to do number 5, but I printed off 2 of these so that I wouldn't have the backside. I really should have just printed it on one side of the page and then I wouldn't have had to deal with that, but what are you going to do? All right. So let x be the random variable of the number of points awarded in a particular game. If the expected value of x is 35 and the standard deviation of x equals 3, what is the total amount of points you'd expect to get if you played the game 5 times? So this one, really straightforward. You're just playing the game 5 times. So the expected value of one game is 35. So I don't really think we don't even need to use notation on this one. Especially if you're using an equal sign randomly. 35 multiplied by the 5 games that you're playing. We don't really need to worry about the standard deviation in this. We can just say we're playing the game 5 times. That's 5 independent games. So 35 times 5 is going to be 175. Yet again, you could argue that as you play the game, you'll get better, and therefore your expected value is going to change. However, we're saying it's the expected value is consistent. So 175. After that, if this game is played 40 times, the distribution of the sum of points can be assumed to be normal. What is the probability of the sum of points from 40 games exceeding 1,420 points? So this is going to be a little bit weird. First of all, the expected value is really, really straightforward. The expected value of 40 games of 40x is simply the same thing as 40 multiplied by the expected value of x. Basically, when you're multiplying a single number for these expected values in questions that are like this, you can just pull that 40 out, not really worry about it, just like we did on this one. So it's going to be 40 times that 35, and that is going to be our mu, right? Our average value that we're going to be using for our normal distribution. So 40 times 35, why am I using a calculator? It's okay, it's 1,400. The real problem here is figuring out that standard deviation formula. So the standard deviation formula that we went over in class, we said the probability of x plus y, we did this one in the previous question too, is going to be the first one squared plus the second one squared. The deal is that we don't have just 2 things, we have 40 of them. So we're going to have 40, but they're all the same, right? So in this case, we're going to have the square root of the standard deviation of the same one squared plus the standard deviation squared plus the standard deviation squared plus dot dot dot, and we're going to have a total of 40 of these. So in other words, we are going to have the square root of 40, and then when you have times the standard deviation of x squared, kind of like this. But the standard deviation of x squared, you can distribute the square root when it's all multiplying. So it's really the square root of 40 times a single standard deviation. And that's the key idea for this question, is that you can just take the square root of 40 out, and that's going to be our overall standard deviation. So our standard deviation for this particular problem, I'm kind of running out of room, so I'm going to do it right here. Our standard deviation of our 40x here, and that should have been a 40x2 over there, I guess, is going to be our square root of 40, then multiplied by the standard deviation. Originally, the standard deviation was 3. So this one was 3. And that happens to be 18.9737. Okay. Um, Recap. We are trying to do a normal distribution, so we're going to be using our normal CDF, so we have to find the mean and the standard deviation. The only formula that we actually did in class was this one, where we're adding 2 standard deviations together, but here we're adding 40 standard deviations together. But they're all the same standard deviation. Because they're all the same standard deviation, we can simply say the square root of how many times we're doing it times the overall standard deviation that is real, which is just 3 in this problem. So we do the square root of 40 times 3, and we get these two numbers. Finally, what we're actually going to do, you're find the probability of these 40 games. So what we're actually doing here is going to be the probability of the overall of 40x being greater than 1,420. So in this one, we're going to be doing our normal CDF. Same exact normal CDF. We need to be bigger than 1420, and then our upper bound for this one is just going to be basically infinity. I said 999 earlier, but because it's 1420, we're going to need much more than 999. So I did a couple more nines there. Our average here we wrote down was 1,400. And our standard deviation, we can actually type it in perfect, right? We can do square root of 40 and then times 3 to make it a perfect answer. Let's do that. Perfect answer there of 0.1459. There it is. We're done. All right, question number 6. All right, at a particular college, all exam scores are approximately normally distributed. The biology exam has a mean of 83 and a standard deviation of 4. Physics exam has a mean of 72 and a standard deviation of 9. If a student got a 90 on both exams, in which exam did they do better relative to their peers? Again, a super common question on the AP exam, and we're going all the way back to chapter 1 on this one of our z-scores. So anytime they're asking about this relative kind of stuff, they almost always mean z-score for a question like this. So our z-score formula, just in case you forgot, is going to be our original score minus the average divided by the standard deviation. So for this particular question, the student's biology exam will do our z-score for biology. Z-score for biology is going to be the actual score. Got a 90 on both of them, right? So you got a 90 minus the biology mean of 83 divided by 4. Throw that into our calculator. I'm just going to do it in my head. 90 minus 83 is 7. 7 divided by 4 is 1.75. And then the z-score for the physics exam is again a 90 minus the 72. But standard deviation is 9. So in this one, 90 minus 72 is 18. 18 divided by 9 is 2. So because the z-score is higher for the second one, we're going to say the physics exam is the one that the student did better on because of that z-score being 2. Number 7, describe the differences between simple random sample, systematic random sample, cluster random sample, stratified random sample, convenient sample, voluntary response sample. So the idea is on the actual test, it's going to tell you which one of these is a cluster sample, which one of these is a stratified sample, and you have to answer them. So for our simple random sample, this is the most basic one. We just call it an SRS. I don't have much to say about it, but it's clearly random throughout the entire population. Every single person in the population has the same chance of success. So SRS, all subjects have equal chance of being in the sample. And if you already have these written down somewhere, you don't need to like rewrite them down, you know? All right, SRS is all subjects have an equal chance of being in the sample. Oh my gosh, my handwriting is so bad. I'm going to write bigger on the next one. I apologize. All subjects have equal chance of being in the sample. I didn't even write the whole word. Oh my gosh. We're on the struggle bus, guys. All right, in the sample. The next one is the systematic random sample. So systematic. A systematic random sample is going to be a situation where you randomly choose the first name. So random choose the first. Randomly choose the first. And then you have a system for choosing all the ones after it. Then system after. And when I say system, I'm talking something like every third person, or every fourth person, or uh prime number following, so prime number after, or something like that. So you basically just you have some kind of system after you've decided the very first one. A cluster random sample is going to be specifically area based. So you select a bunch at a time in a given area. My favorite example that we did of this earlier in the year was when I had you guys grab a handful of candies out of the jar, or the bowl or whatever. You grabbed the handful of candies and you grabbed from one section. So you got a cluster in that one section. Another example might be you select 3 buildings in the school. So you select the 100s and the 800s. So you clustered those 2 different groups. So a stratified sample is going to be one where you have uh, divided the population in advance according to criteria. Divided population according to criteria, then proportionally selecting. So, for instance, I apologize. Divided population according to criteria, then proportionally selecting. So you're dividing population according to criteria and proportionally selecting. So you divide it according to, say, the score they got on their last math test. So you've divided it into kids who got A's, B's, C's, D's, and F's, and then you figure out what the proportions are for those people within the population, and you select a certain portion from every group so that you have a representative sample of the group. You could also do it by a bazillion different criteria. You can do it by something like skin color or hair color or height or your gender, or whatever it is that you want to stratify the population by, and ask questions based upon whatever is going on. Last but not least, our last 2 to talk about: a convenience sample. A convenience is something like, literally it means convenient. So I don't really think I have anything to write there of a definition, because it's kind of in the word itself. But a convenience sample is when you pick like the first 10 people who walk in the door. Done. Something easy like that. Involuntary response, I also don't have anything to write down, because it's people who get to respond voluntarily. So anytime you get like a survey in your email, or a survey at the bottom of your receipt, all of those are voluntary responses, because you just decide if you want to or not, and they are decidedly not random. Okay, finally done with that. And now we are on to question number 8. And I think question 8, I won't have to do any fancy paper stuff. Here we go. Question 8, a large fancy high school has 8% of its students go to Ivy League schools. If 15 students are randomly selected, what's the probability that most 2 of them go to an Ivy League school? So in this situation, we are going to do our binary check one more time. So I'm not going to write out the whole word, but again, this is a binary situation. I'm going to tell you on the actual test, it'll be a binary situation for this question. But the idea is your binary is you have 8% of the students, because 8% is going to be not because 8%, because this is a large fancy high school. You're going to assume that this 15 is less than 10% of the population of the school's population. So there's more than 150 kids at this particular school, and therefore it's independent. It has a yes or no chance you either go to Ivy League or you don't. The number set in advance, 15. The probability set in advance is 8. What is the probability that most 2 of them go to an Ivy League school? So this is saying, what is the probability that x is less than or equal to 2 for a binomial situation? So all we have to do to make our life as easy as possible, you could do the fancy thing. I said easy as possible, and I said then I'm picking the hard one. But the hard way is writing it like this, where you write the sum from 0 to 2 of how many 15 students are selected, and because you're going 0, 1, 2, and then you have 0.08. Be careful there. 8% is 0.08. I multiplied by 0.92 to the 15 minus I. So you could just do it that way, or the better way to binomial CDF on the calculator. Binomial CDF on your calculator. Please use that button. It's your buddy. So second vars binomial CDF, boom, right there. And our number of trials that we're doing here, we have 15. Our probability of success is 0.08. Our X value is 2, and that is it. We're done. It turns out there is an 88% that at most 2 of them go to the Ivy League school. So looks like we got 8870.8870 in our calculator. Boom, done. What is the difference between an observational study and a well-designed experiment? So the biggest difference is that these ones, the well-designed experiments, can show cause and effect, whereas observational studies can only show correlation. So we're, if you have a well-designed experiment, you could say this thing causes the other one to happen. If you have an observational study, you can only show that 2 things are related to each other. FRQ number 1, no bins for binomial. I've already made you write that down one more time. Just a reminder, binary independent number of set in advance, success chance is consistent. Dependent probabilities akin to this. If 25 pieces of paper are placed in a hat, each numbered 1, 2, 3, 4, all the way to 25, and 5 different pieces of paper are drawn, what is the probability that all 5 are even numbers? So you're drawing 5 different pieces of paper, so there's no replacement, and you want to know how many of them are even numbers. So first of all, out of these from 1 to 25, there would be 12 even numbers, and there would be 13 odd numbers. So the chance of the very, very first piece of paper being drawn being an even number must be 12 out of 25. But we want to know how likely is it all 5 are even numbers. So once you've drawn 1 even, there's only 11 even numbers left, and there's only 24 pieces of paper left in the bag. And on the third draw, you have 10 and 23 left, and 9 over 22. And I think you can see this pattern nice and easy. So let's actually just do this on the calculator. So we got, I'm going to put a parentheses, 12 times 11 times 10 times 9 times 8. And the parentheses divide, new parentheses, 25 times 24 times 23 times 22 times 21. And it turns out that this is about a 0.0149 probability, or a 1.49% chance. So that's a pretty low. C and D would require logical thinking. Remember, less than 5% is very unlikely, and extrapolation is a thing. So that's kind of what this free response is going to be like. So because I got a result that is less than 5%, I can say that it's very unlikely, and it's probably not the case. If it was a number bigger than 5%, if it like 6%, it's unlikely, but it's not like so unlikely that it's never going to happen. And extrapolation is a thing. So extrapolating really means that you take one part of a population and you use that to describe the rest of it. All right. Letter A, conditional probabilities similar to this. A study center has 2 different plans, Plan X and Plan Y. Plan X costs $100 and has 75% chance of success. Plan Y costs $60 and has a 60% chance of success. If your goal is to succeed while paying the least and you're willing to try both plans, should you try Plan X first or Plan Y? And what is your overall chance of success? Show your reasoning using expected values. Okay, so let's say you have, let's do a little tree situation. So let's start with Plan X on the tree. If you start with Plan X, you have spent $100 and you can succeed. And you will succeed using this at a 0.75 rate. And in this situation, you have spent $100. And you have succeeded, and it will happen precisely 75% of the time. After that, you also have a 25% chance of going into Plan Y. So if you go into Plan Y, you now have a 60% chance of succeeding. So this is either way, you're spending either way you're spending 100, right? So I don't really need to write that twice. But if you go to plan Y here, you have a 60% chance of succeeding. And if you do succeed, you ended up spending $160, and you have a 0.4% chance here of also spending $160. So we want to know, what is our overall chance of success? Well, if you succeed right away, that's good enough. Your overall, and then if you're, can't speak. If you don't succeed on the very first try, you're going to have to spend more money. So you have a 75% chance of spending $100. So we'll write this twice. So our very top one is our probability, and this bottom one is your expected value. So your probability is going to be 0.75 plus, and you're going to succeed 0.25 times 0.6. Because only 25% of the time will you actually go into this other version of work here. So adding these up on our calculator, can I do that in my head? Should be 9.9, I'm pretty sure, but I want to double check. So it's going to be 0.9. And your actual expected value is, well, 75% of the time you will end up spending $100, and 25% of the time, regardless of whether you succeed or fail, you will end up spending $160. Because remember, you already spent the 100 after you failed, and then you had to do it again. So we have 0.75 times 100 plus 0.25 times 160, and that's going to be your expected amount of money if you try plan X first. It'll be 115. You're doing exactly the same thing for plan Y first. If you do plan Y first, you have a you're going to spend $60 with a 60% chance of success. So it's going to be $60 with a 60% chance of success, and you succeeded and you spent $60. And 0.4% of the time you're going to go to plan X anyways. If you do the plan X here, you have a 75% chance, and on this one you spent again that $160, and 25% of the time you still spent $160 and you failed anyways. Yikes. Okay, so what's this one? Your probability of success on this one is going to be 0.6 plus 0.75 multiplied by 0.4. So let's find out what your chance of success is. 0.6 plus 0.75 times 0.4. So you have 0.9, and that's kind of expected, right? Because regardless of whether you try plan X or plan Y, if you try both of them, you have a 90% chance of succeeding. But let's see, is there a difference in the money? So 0.6 of the time you will succeed immediately, and you will end up getting spending $60, and then you'll be adding that to some portion of the time. This specifically the 0.4% of the time you're going to be spending $160. So let's see, is there a difference? See, 0.6 times the 60 plus 0.4 times the 160, and you can see this way you're going to spend $100 on average, which is interesting. So either way, you have a 90% chance of success, but plan X first has $115 and plan Y costs you $100. Now you might say, I'd rather choose plan X because I might succeed right away, then I don't have to do both study plans and it will save me time. That wasn't the question. The question was asking which one is going to save us more money. Doing the cheaper plan that has a lower chance of success in this setup is going to have a less money effect. I'm done with this video. Have a great rest of your day. Peace out, guys. Good luck on your finals.